So I'm actually giving another talk in 2 weeks, which is an introduction to this book. And if you guys want to, for those who don't really know what machine learning is, this talk might be a good introduction to the second talk. So let me start with some type of disclaimers. First, I did spend 3 years of my life on the book, but I'm not a machine learning expert, just because machine learning is a very wide field. So it's really hard to touch pretty much anything that exists in machine learning. And I don't want to sell machine learning to you guys. So I don't say that machine learning is a solution to any problem that exists in the universe. Not at all. So I have only one goal. And this goal is I'm hearing that so many times. People say, we have used statistical machine learning tools too, and the others are like, ooh, statistical machine learning. And I'm like, yeah, so what? It's statistical machine learning. It's nothing really special. It's pretty straightforward. So my goal is to convince you guys that machine learning is not that difficult. So that's the definition of machine learning. Machine learning develops algorithms for making predictions from data. Kind of simple. There is one word that is kind of a little bit, the word predictions, right? So are we talking about psychics here or something like that? No, we are talking about the statistical sense of the word predictions. You would say, you know what? I know statistics, I know data mining, and statistics is doing pretty much the same thing, making predictions from data, and data mining is doing pretty much the same thing. So what's the difference between machine learning and all those fields? And I would say, you know what, guys, those fields are very, very, very close to each other, essentially. They're not that different. So machine learning, I would say, it's somewhere in between statistics and data mining. From which perspective? So statistics develops methods, or I would say models, that explain the data. And those models are not necessarily in context of a special task that this model is trying to solve. Not necessarily. Vice versa, in the case of data mining, you actually have a task, a real-world task that you want to solve. And you don't care that much about which method you are using to solve this problem as long as the real-world problem is solved. So machine learning is somewhere in between. People who practice machine learning develop tools, methods, with a particular task in mind. So again, machine learning is about building algorithms for predictions from data. So we'll be talking about algorithms, we will be talking about predictions, and let's start with the data because that's the most fundamental part, right? So what's the data? For people who think about the data as a content of a database, that's what I pretty much mean by data. So basically you have records in a database. In machine learning, those records are called data instances. And you have columns, right? And those columns are, in machine learning, we say those are features. So a data instance is represented as a vector of features. Let's take a look at this feature, this data instance. So how would we represent that data instance as a vector of features? That's one option. 2 numbers. Who cares what those numbers are, right? I explicitly didn't write what they are, but if you really want to know, it's like my height and my weight probably 10 years ago, something like that. So look, it's a data instance and 2 numbers, right? That's the representation. Here's another really, truly great data instance, and it's a representation as well. And you're like, 2 numbers, not too many, right? Can we add some more features? I'm like, no problem. Let's put my blood pressure on it. Why not? 2 more numbers, right? You're like, 4 numbers is not enough? No problem. Let's take my blood pressure every day and put it in the system. And you're like, that looks long, right? Many numbers out of the sudden. So what? So why do we need all those numbers? We can put like really zillions of numbers in this vector. Why do we need all those numbers? And I'm like, yes, that's exactly the question. Why do we need those numbers? So in machine learning, we build those feature vectors that are specific for the task that we have in hand. So if our task is to, say, predict whether I'm at risk of high blood pressure, then this feature vector is just beautiful, right? That's exactly what we need, more or less. My weight, my height, and my blood pressure measure, something like that. But if the task is more like, say, face recognition, right? To say that this face belongs to Ron Bekkerman, this face belongs to Michael Jordan, those numbers are just not helpful. So the first takeaway is features are important. Features need to be defined for a particular task. So what is machine learning all about? Machine learning is about building a compressed representation of your data. Let's say that you have like a terabyte of data, right? It's a terabyte of stuff sitting somewhere. You need to kind of express what you have in your data in a compressed form in order to use this in the future for essentially making predictions about new data instances that you have in the system. And an example here is that you have a terabyte of data. A compressed representation would be to say, we have 25 groups of things in our data, and the prediction would be to have like one new data instance to arrive, and we'll say, what, this data instance belongs to group 5 or something like that. That would be an example. So machine learning actually consists of only 3 basic methods. There are many others, but they kind of fit in this framework pretty well. So the first big subfield is called classification, and that's something that I'll be covering mostly this talk. And the idea is that you are given data that you know that this data belongs to particular groups. Let's say that you have each data point here, each dot is, say, a document. And you know that, say, green dots are documents about politics, making it up, and red ones are documents about sports, something like that. So you know which groups your data instances belong to. And then once you have new data instances, I have like a blue one over here, blue one over here, you don't know what group they belong to. You need to infer in which group those data instances will sit. That's the classification. Clustering actually looks kind of similar. So we have the data, and we need to infer which groups we have in the data. So we don't necessarily talk about like documents about politics or sports or whatever. We just need to figure out which data points sit kind of close to each other in the data set, something like that. Admittedly, not well defined, and we'll discuss it later. And the third big area of machine learning is regression. And so I'm actually not an expert in regression at all, so I'll just mention it. I won't cover it in this talk. But an idea here would be, you have those red data points, right? They kind of look like as if they're sitting on some line with a certain slope, something like that. So you basically try to fit a line to the data points that you have in the system. And fitting a line, it essentially can be considered as more like, say, ranking of those data points, something like that. You would say that the upper one is like number 1, then number 2, number 3. You just consider the projection of those data points on this line, and you would come up with the ranking. So that's another approach that is very popular in machine learning. So here are two strange considerations. It really looks like I have like circles here and here, so like classification and clustering are very similar. Not at all. And the difference is that we know the classes a priori in classification, and we don't know the classes in clustering. I'll talk about that later, essentially. It's an important point. And it looks like classification and regression are very different. You know what? Not at all. The methodology that you're using to solve both problems are actually pretty similar. So in classification, you would say, I have a more confidence in this data instance to belong to this class. So you kind of come up with some type of ranking as well. So that's a little bit of an intuition. What's the difference between these three fields? So what machine learning is not? Machine learning is not an exact science, meaning that if you build a machine learning algorithm, it will not work in 100% cases. And here, let me give you like a little bit of a brain teaser here. Here's an algorithm. Yeah, let's say that it's a machine learning algorithm. So our task is spam detection. Say like, this email message is spam, this email message is not spam. And let's say that the output of the system will be 1 if the email message is spam and 0 if the email message is not spam. And let's say that we have an algorithm that works in 90% precision, which essentially means, in this case, that the output of the algorithm will be in 10% from the optimal, from the correct one, essentially. And here's my input, 5 email messages, and here's my output. So those numbers are not 0 and 1s, right? But we know that the algorithm produces the results, which are in 10% from the correct one. So given this number, 0.96, can we say that the message is spam or not spam? It's close to 1, right? So it's in 10% from 1. So it is definitely spam. This is not spam, 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 no, not spam. And it works in 100% cases. What's that? So is machine learning exact or not? You know what? I tricked you. So when I say that the algorithm works in 90% accuracy or precision, I essentially mean that there is 90% chance that the algorithm will succeed, right? So what essentially means is that if we had these 5 email messages that I showed to you, the chance that we'll succeed in 100, so the algorithm is exact, is essentially 0.9 in the power of 5. And the more data instances we have, the less chance is that we are totally exact. So is machine learning an exact science or not? Give me an answer. No, it's not. Is it that bad? You know what? I'm actually not seeing anyone move, getting out of this room, but like an old school computer scientist would just leave. An old school computer scientist would you're wasting your time in developing non-precise algorithms. It's just nonsense. Who will use an algorithm that it doesn't produce the exact answer? What is this? If if you go to a bank and you deposit your $100 in the bank, do you want the bank to say that, we'll keep your money in like 60% chances? And if I deposit my $100, in a bank, I want my $100 to sit in the bank, and I also want my fixed rate interest on this $100. Exactly. So that's what people usually say. You know what? I'm like, let me give a little bit of perspective here. So here's the bank. And here's this happy investor. He's just deposited $100 in a bank. And the bank keeps his money. The bank, it's not bank's money, it's the guy's money. The bank keeps the money, right? And the guy is very happy just, walking to his car through the parking lot. And while he is walking through the car, to his car, he actually made a little bit of profits. I would say not that much profits on a fixed rate interest, but he was just working, right? At the same time, the bank took his $500, invested it in a stock market, applied the best of machine learning in doing online trading, the best machine learning algorithms possible, and got $100 profits. So I'm not asking who is the smarter here. I'm not asking who is richer. I'm not asking questions like that. The only thing that I'm trying to say is that imprecise algorithms work and make money. It's worth investing time and effort in developing those algorithms. So is it that bad that machine learning is not precise? Tell me, is it? It's not. Questions so far?
Just one clarification. I know you didn't mean it that way, but a statistician here would really get mad, because in that perspective, if you say machine learning is not a science, that would practically mean statistics is not a science as well. I know you didn't mean it that way, but it feels like it leads to that way. I just want to make
sure, yeah.
Statistics is a lie.
I'm not
that is
politically correct.
But it's
well, I definitely didn't mean that. And I love machine learning, and definitely machine learning is, well, I consider machine learning as a part of statistics, actually. I'm more a data miner because I want to apply machine learning methods to existing problems. But machine learning is a part of statistics, definitely. So let's start talking about classification. It's like a big chunk of my talk today. So in classification, you have two phases. One is you are given what we call label data. So we know that those are documents on politics. We have the document, the text, and we have the label, which is politics. We know that those documents are on sports. We know that those documents are on Medicare or something like that. So we have the historical data. Someone gave us the labels. And at the training phase or learning phase, you essentially build the model or a classifier. And to be honest, it doesn't really matter how this classifier looks like, but I'll show you a few. And you have the next stage when this classifier has been built. You essentially need to apply it to a data that you don't know much about. So you're given a data instance or many data instances, and your output needs to be a label, or essentially, is this document about politics, or this document is about sports, or something like that. So where's the voodoo? Do you guys see where's the biggest problem here? Do you have any answer for me? Looks very like, if you said that the problem is how to build this classification model, I would say no, because you just download an open source and it does it for you. The voodoo is in getting labeled data, right? Where do we have this historical data? Who tells us that this document is about politics and this document is about sports? So that's the most important part. If we have the label data and a lot of label data, guys, we are all set. We will solve any problem available in the universe. So two ways to get the data. One is implicit feedback. Like our LinkedIn users basically click on something, and if they click, we can register it, and we can consider it as like a positive example. We can consider some of negative examples, something like that. So we can use this implicit feedback to actually train our models. Another one is to crowdsource labels. So we can use Mechanical Turk. I don't know if you guys are familiar with those services, but you just give out 10,000 data instances, and they will just label those for you and bring it back labeled. So two big troubles here. One is the data quality. If those Mechanical Turks label your documents and produce some kind of nonsense, and you feed it into your model, you end up with total nonsense. Garbage in, garbage out. It's a very important thing to remember. Another part, your data can be not well representative. What I mean is that, I can give you an example. So let's say that we want to come up with some type of reputation score of LinkedIn users. And we build it upon recommendations that we have on the profiles. So whoever has more recommendations is like more important person, something like that. You know what? I don't think that it's the right approach, because whoever writes recommendations is essentially a very small and kind of not representative portion of LinkedIn site. If we want to build a whole model based on that, our results will be very skewed. So that's why we really need to be careful if we want to work with what's called explicit feedback. If people tell you, I like it or I don't like it explicitly, you need to be really, really careful, because not many people do that. And whoever does this, it can be the case that it's a very special type of population that have their own incentive or incentives or something like that. So is it worth the hassle? Do we still want to do classification? You know what it is worth. So essentially, I can give you like one example. In 1995, I was working for this startup that was doing handwriting recognition. And we were trying, machine learning wasn't really around, so it was, but we weren't really aware of it. And so we were trying to come up with some heuristics, how to figure out which digits or letters, like it was very complex. Didn't work that well. And then we hired one guy who knew what neural nets are, neural networks. It was like one of the first classifiers. And he just applied it to our data, and you know what, out of the sudden we started getting decent results. And it was back like 17 years ago. Oh my goodness. So like it's worth it, it's still worth it. So I have a running example that is really silly, but you know, you will see that it's kind of easy to show it on a two-dimensional space of the screen. So I apologize in advance that my example is really bad. So I have people who are represented as dots in the space of their height and their weight. And what I want to say is like, to infer which people are good at basketball and which people are bad at basketball. Basically saying that whoever's tall is slim is good at basketball, something like that. So we have some historical data. We know that there are some people who are good at basketball, and those are their measurements, right? So their weights and heights. And some of them are not good at basketball. So this guy will be somewhere over here, and this guy will be somewhere over there. And what we need to do is, given these new data instances, blue ones, unknowns, we need to say whether this guy is a good basketball player or not. There is the very simple classification algorithm that is called k-nearest neighbors. And it does a very simple thing. For every blue dot, it kind of draws a circle around it, like finds a neighborhood, and decides on label of that dot based on labels that are sitting in this neighborhood. So that one will become red, and that one will become green. Very simple. Like, do we need machine learning at all? It's like it's solved, right? So do you guys see the big problem here? What is really bad about this algorithm? Not complete. That's right, but like the problem, at least the main problem that I'm seeing here is that in order to compute this neighborhood, you actually, for every data point, test data point, you need to make comparisons with pretty much the entire data set that you have. And think about, like, you know, a million data points in your label data set and a million data points in your test data set, that stuff. So people have come up with many heuristics and many smart algorithms to overcome this problem. But anyhow, like, if you have a data point and you need to scan the entire data, or at least a portion of the data to decide, that's not is not going to scale, right? And machine learning is definitely all about scaling. Here's my favorite classifier of all times. It's called support vector machines. So it's basically, the idea here is that you want to build a line or a hyperplane, people call it hyperplane, that would separate green dots from red dots. Very simple. And the question is how exactly you want to draw this line. So it doesn't look like this line is a good line. Let's draw a good line. That's a good line. You know why? Because it is on the maximum distance from red dots and from green dots. It's called maximum margin classifier. And you know what? The slope of this line actually is defined by only 3 dots. This one, that one, and this one. So those dots are called support vectors. And once this line is drawn, all you need is, given 2 data instances, you just see whether this instance is to the right of the line or to the left from the line. That's all. Very simple. That's how you classify. Where's the voodoo here? Looks very, very kind of intuitive, right? I really love this classifier. But do you know what the problem is? Outliers, yeah. We'll just see. So the main problem actually that to draw this line, you apply very heavy constrained quadratic programming mechanism. So the math behind it is actually pretty complex. And here, let's start looking into some special cases that we need to cover here, because our data doesn't look as beautiful as I definitely drew it on the screen, right? So some data is not what's called not linearly separable, meaning that there is no straight line that would separate between those dots. So what do? You know what? SVMs are really good at solving nonlinear classification problems. And the best news ever is that the complexity of an algorithm like that is not getting dramatically increased if we are moving from linear methods to nonlinear methods. It's very important in many cases, actually. So another problem, your input data, your label data can be so skewed in size. Look at that. I can find my positive instances. Just a few of them right over here. So that looks kind of problematic, right? You know what? SVMs are doing a very good job. So basically, once you draw this line, all matters is those dots, right? So you kind of can ignore all the rest. So SVMs they actually can cope with this problem pretty well. I am definitely filtering out some details here, but anyhow. Another problem, let's say that our problem is not binary. So we have more than 2 classes, politics, sports, and healthcare, something like that. How can we cope with that? You know what? That's not a line. So SVMs are not good at it. So they can, well, there are techniques, quite a few. But SVMs are just not very good at it. So you need to work hard to resolve it in some way. Here's another problem. Your data can be so multidimensional. Look at that. That's one of your data instances. And you know what? You only have like 160 dimensions or something like that on this data instance. That really looks pretty much as real-world data instances that we're seeing. They're usually long and very sparse. So many numbers are just zeros. It's just, you don't have this feature or something like that. Here's another data instance. And now, can you tell me whether those 2 data instances are similar to each other or not? Looking at that mess, right? Actually, they are similar. You know why? Because only in one spot over here and over there, numbers are not 0. And because of that, only because of that, they're kind of similar. So it's kind of silly, right? But that's the real-world problems. Usually, we have not 2 dimensions and not 100 dimensions. We have 100,000 dimensions. We need to cope with that. what is important to know is that we are thinking in 2 dimensions or 3 dimensions. Our brains are not open to 100,000 dimensions, meaning that if you want to try use your intuitions about how would you solve this problem and try to doing something with your hands, forget about it. This space just looks completely different. But for SVMs, it's actually good because once your space is so huge, it's so multidimensional, it's kind of easy to do this linear separation. You will find a hyperplane that separates classes, even if they look that messy, just because we have many dimensions. That's something else that I wanted to mention. So to summarize about SVMs, when do we use them? We use them when we don't have that much label data. Basically, to train an SVM classifier, it's pretty heavy. I know that there are algorithms that try to overcome that, but you know what? It's still heavy. I know that from my personal experience. If you have some geometry in the task that you're working on, say machine vision, right? Machine vision is processing pictures. It has some geometry. If you have it, SVMs are really good. SVMs are also good at text, but if you have the geometry in your task, then they are much better even. If you want very high precision, you want to spend a lot of time on training this model, and you really care about precision, try SVMs. And they will not work right away. So you will download it in open source, you will run it, it will produce you 0 accuracy. But then you will tune the parameters, and out of the sudden you can get to 90 or something like that. Let's talk about a different classifier here. It's called decision tree. It's a very simple classifier, essentially. You will see, it's totally trivial. So you build some type of a tree, and each node you have a question. For example, in my running example, if the guy is taller than 6 feet. If no, you say, no chance the guy will be good at basketball. I'm definitely, I hope that I'm not offending people here, but it's a silly running example. So, and if your weight is below 250, you say, you're tall and slim, you can play basketball, something like that. So looks very simple, right? And definitely you can understand that it doesn't work in 100% cases. I would say probably not even in 50 or something like that. But where's the voodoo? Do you see that where we need to invest energy here to solve this problem? Essentially to set up those thresholds, right? That's what we learn in the learning phase, right? Let me give you an example that is actually kind of real world. I have talked about handwriting recognition, and so we have digits. Please welcome my right hand and left hand. And we want to say that, those pictures are actually the digit 5, and those ones are digit 2 or something like that. That's the task. And you know what? I promise you that by the bottom of this slide, we'll solve the problem. I'm definitely excluding quite a lot of details here. Let's start with features. We need to build feature vectors, right? You remember. That's what I propose. Let's work with circles and hollows with openings to the right, left, or up. That's 4 features that I'm working with. Take a look at this beautiful 5-letter digit, right? So you actually have a hollow that opens to the right, and another one on the bottom that opens to the left, right? That's the intuition behind these features. Let's map them on your digits. Actually, they map pretty neatly. Look at that. Let me remove the digits just to take a look at the features, how they look like. You know what? If you look at something like that, kind of looks like 3, right? So we're abstracting out some details, right? So look what's going on. So we have those features. Let's just redraw them to look beautiful. Let's add an empty symbol for those features that don't exist. And out of the sudden, we have beautiful feature vectors of 2 features. For every digit, we have 2 features. And I want to you to look at the 4. So we have a feature which has this opening to up, and that's pretty much the only feature among all of them like that. So we don't need a feature that appears only one in the data set. Who cares about this feature? Let's say that it's empty. We don't care about it. So those are our features, and let's build a decision tree. So we're asking, on the bottom of this picture, do we have a hollow with an opening to the left? Okay, that's question number 1. On the upper part of this picture, do we have a hollow that has this opening to the left? If both answers are yes, we have the 3-letter. If the second answer is no, then do we have a hollow that opens to the right? And if yes, then we have 5, letter 5. That's how we solve the problem. Look at that. We have just recognized letters, digits, handwriting. Not too difficult, right? 1 slide, problem solved. Where's the voodoo? Yes, so that's essentially like that's the direction, right? The voodoo in the features. You need to choose the right features. You need to find those features on the pictures, which is not trivial at all. If you find the right features, you know what? The classification problem is simple. And it's actually really important for LinkedIn. Our data is beautiful. It's very clean. If you find the right features, you don't need to invest in machine learning that much. That's one of the messages that I wanted to have. And there are many techniques to find good features. Feature selection, feature construction. If you're interested, we definitely can talk about that. So a decision tree actually doesn't work that well standalone. But what people are saying, why don't we just take all decision trees available, many decision trees, build an ensemble of decision trees, or what's called a forest, and apply all of them to the same data point, and then just use a voting mechanism. Look at that. I have like 3 decision trees here. Do you know what is the problem that I'm trying to solve with those decision trees? Obviously, whether the word Obama appears in a document or the word Romney appears in the document, is the document about politics or not? That's the problem that I'm solving, nothing else. You understand that? And I have an advice for you. If you want to win $1 million, just take all the classifiers that you can imagine, throw them together in one big ensemble, and you'll get the money. That's how people actually won the Netflix prize. I'm definitely extracting quite a lot of details, but that's the direction. And another important approach in decision trees is that how essentially you build these decision trees. So you have like a few of them in the system. What you need to see is which portions of your training data have not been covered well with the set that you have in hand, and go there and build decision trees that cover this portion. You kind of try to cover the whole space that you're working with. That's called boosted decision trees. And you know what? Once you build many trees like that, I'm literally talking about probably millions. And once you are using this boosting approach that you try to gradually cover the whole space, then it's like the best method in the universe. It's actually a very powerful method. That's how people solve web search down there with our friends in Google. Well, I don't know really for sure, but I'm pretty sure. When do we use those boosted decision trees? In two cases. When you have a lot of data, a lot of features, say all the text, all the words that are available in the universe, you can use those decision trees because you will build a tree per feature, more or less, something like that. Another point, if you have many, many classes, it's like politics and healthcare and sports and whatever, and you have like thousands of them, use them. They are very good at it. What they're not really good at is if your data is very skewed in size. If you have like 1 million data instances, negatives, and say 10 that are positives, you know, they will not solve it. So all the decision trees will just say no, 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 no. You will not have even one single one that will say yes. Well, again, probably, you know, it's hard. It's not trivial. So let's talk about the last classifier that I have here. And it's called logistic regression. It's very popular. It's actually, so you remember that I had classification, clustering, and regression, right? This one is called logistic regression, but it's actually a classification method. So the terminology is complex, and why it's so complex? Because the underlying technology is the same, both for classification and regression. So people it's kind of hard to separate those topics. And here's my first and I guess the last formula in this talk. So basically what you do is you estimate the probability of a guy to be good at basketball. And it's not just the probability, it's what's called the odds. It's the ratio of probability of a positive event and the probability of a negative event. So these odds, it's actually proportional to just a linear combination of your features. It's very, very simple, just a linear combination. And if you want this equation to be exact, you just need to add log to this equation. It's just because your probabilities need to be between 0 and 1, and you have many, many interesting, nice features if you actually add this log over there. That's the whole model. And where's the voodoo? The voodoo is just to learn those coefficients, right? C1 and C2 in my case. And the intuition here is more like, you know, we want people, if we want a person to be good at basketball, we want the person to be taller, right? So C1 is the coefficient of the height, needs to be positive, and we want the person to be kind of slimmer, so C2 needs to be negative. Something like that, very, you know, hand waving, not precise, but that's pretty much what this classifier is all about. When do we use logistic regressions? First of all, if your task has something probabilistic in it, it's nice to use a probabilistic method in this case. And also incorporating prior knowledge in a probabilistic method is pretty straightforward. When the number of features is not big. So basically what is good about logistic regression, it tells you this is an important feature, this is a less important feature, this is more important, this is less important. If you have like a few features, say hundreds of features, it's very nice to take a look at them and see, yeah, it makes sense, this feature is important, yeah, it makes sense that this feature is not important, something like that. If you want to train the model really fast, the training of a logistic regression is pretty fast. And if you don't really care about precision, you know what, logistic regression is just not the best algorithm from the precision perspective. But in some cases, people say, you know, I have 85% precision, you want to bring me 90 with a very fancy model, I don't care, 85 is good for me. So that's how it works. Questions? Yes?
Yeah, I had a question about the components of the feature vector and the correlation between them. Is it better if you can find a feature vector where there's no correlation between any of the components in there? Because height and weight are kind of a strange thing. There is some correlation there, right? In general, you could say, you know, the taller a person is, the more they're going to weigh.
Yeah,
and
that's right.
And there's some limits there.
Yeah.
But if we look at certain, you know, feature vectors on LinkedIn, there may not be any relationship there. And
yeah, so that's essentially, you are basically talking about the paper that we submitted the day before yesterday. So we are using logistic regression for re-ranking NAS by relevance, and we are taking the correlations between features into account. So the model is good enough to actually incorporate those correlations, and it improves. So like the simple model is really trivial, but you really, what's nice about logistic regression is you can improve it like, you know, like unbelievable. You can build a very complex method based pretty much on the same idea. So if you want to talk about that, we'll definitely talk later. So I actually have only 10 minutes to cover my favorite topic, clustering. So I am the clustering guy. I was doing clustering for 10 years. I really like this topic still. I have my concerns because I have my experience, but let's just throw it on you. So clustering, we don't have classes. We don't know that those documents are on politics, those documents are on sports, something like that. We just have data. And we need to find some groups, some coherent groups in this data, something that would say, this is something that looks kind of close to each other, very badly defined. Is it useful at all? Actually, it can be useful. And one of the use cases is, let's say that you are given a lot of data. You're given a terabyte of data. And a person is just asking, tell me what I have in my data. I have just some type of bytes. Tell me what it is all about. So what people usually do, they take the data, they cluster the data, they take a look at the most representative data instances within each cluster, and you will kind of figure out what you have in your data. It's called cluster analysis. It's quite a well-known technique. So clustering is useful in some cases. Let me just show how the simple k-means clustering works. It's like the most common clustering algorithm available. Anyone who is doing clustering pretty much is doing k-means. Well, besides me, I was like trying to show that I can do better than that. So those are data instances, right? Kind of scattered. What I want to say is that it's kind of, we see some type of a cluster over here, some type of a cluster over here, and some type of a cluster over here. What we do first is we set up what's called centroids, the centers of your clusters. And we set them up pretty much randomly. You can use some heuristics, but it can be pretty random. And you associate data points around those black dots that you would say, those are your clusters. And look at that. That doesn't look that beautiful, right? So we had a cluster over here. It kind of is split to two right now, something like that. So what you do then, you adjust your centroid. Centroid will go into the center of mass, essentially, of your cluster, something like that. And then you reassociate the dots. And you see over there we have more, what's the color of this dot? Purple dots. And we do that again. Centroids move to be in the center of mass of your cluster, and you reassociate dots. And out of the sudden, we get those beautiful groups. It's a very simple algorithm. You know what clustering is? It's problematic. It's problematic. You have like too many degrees of freedom, essentially. And here I can give you an example. That's pretty much a real-life example that I was trying to deal with. So you have, like, say, product reviews. And you want to cluster them according to two different criteria. You would say, let's do it by topic. Let's say that this is a product review on electronics or books or baby products or something like that. And you want to take the same data set and cluster it somehow differently, say by sentiment, whether the person likes this product or doesn't like this product. So you basically choose words. In the first case, it would be like, camera or diaper or something like that. In the second case, it will be like excellent, brilliant, awful, evil, something like that. You choose the words, you're trying really hard, you solve this problem, and that's the answer. So you compare your topical clustering with your ground truth on topic, 60%. You compare your sentiment clustering with your ground truth on sentiment, 60%. You compare your topical clustering with your sentiment data, 60%. It's basically clustering will capture all the signal that sits in the data. It can be topic, it can be sentiment, it can be anything. It will capture, but it will not capture it precisely. It will always be kind of really, really shaky. And the question is, why do we need clustering at all? Clustering is inaccurate. So with a clustering algorithm, you cannot get good results. It's just pretty much impossible. if you are choosing between clustering and classification, you know what, crowdsource labeled instances and go with classification. There are a few use cases where you definitely you want to use clustering. And one of those use cases was essentially if you have your feature vector in classification. So the task is classification. You have your feature vectors that are just too long and sparse. You want to cluster features. You want to work with a shorter vector, but this is a dense vector. So if you want to do that, cluster features represent your data instances as vectors of feature clusters, and then apply a classifier. That's what we did like 10 years ago, and actually it was quite a big win. Another use case that I wanted to talk about is like, I don't know if I have enough time. So let's try it. I'll try to show you. So you remember that in Netflix price, right? When we were talking about winning $1 million with classification, I was saying use all the classification methods possible, build a big assemble, and you will win. You know what? In clustering, it just doesn't happen. Let's take a look. Let's say that that's like a space of all possible clusterings of the same data. And let's say that red dots means that those are good clusterings, kind of accurate clusterings. And blue dots means that those are not good clusterings from different perspective. So you run 4 good clustering algorithms. You end up with those clusterings in the space of all possible clusterings. And if you just apply an assemble method, average them together, you end up with a spot that is just not good. Just because in clustering there are so many degrees of freedom, the clusterings that are being built are just too different from each other. You average things that are almost completely irrelevant to each other, you end up with some type of garbage. And our idea was just to improve your clustering algorithm in a way that it will run a few iterations more, but condition each one on the others. Kind of condition all these clusterings on each other, and you will kind of bring them together closer. And since you were using a good clustering algorithm right away, the hope is that you will not actually hurt the results, and you know what, the results were really good. So that's the way to actually come up with I would say, I hope, the best clustering algorithm ever. We published it 2 years ago. It's just, I'm covering some stuff that I'm very I was really passionate about a few years back. Oh, I still have a little bit of time. Let me show you the use case that we were doing here at LinkedIn, which is categorizing job titles by function. And the function is like engineering, sales, marketing, something like that. PR and HR or something like that. What is the traditional approach for categorizing that many titles? You just, choose a few titles, say 20,000 titles, you crowdsource the labels, and you learn a classifier on those labeled data instances, apply it to the rest of the data. Our method is a little bit different. Actually, we don't really use machine learning. Look at that. So first, we extract the most common phrases from those titles. Let's say software engineer is a very common phrase. And then crowdsource labels of those phrases. And then take the whole list of job titles and basically find those phrases and decide on topic based on category based on those phrases. I even published a paper on that. You know what? This is not very machine learning approach, but it outperforms the traditional machine learning. And you know why? Because it's built for this particular task. Don't use a generic method. If you build a method per task, as machine learning likes to do, you will succeed. And you know what? I actually did use machine learning in this framework. I used it for finding inconsistencies in the label data that crowdsourced technology was producing. So people cannot be consistent. And to find those inconsistencies and kill them, you actually need to use machine learning, and it was quite a heavy weight. And you know what? It was a big success because we improved from 80% precision to 95% precision. And if you tell me that you know like one single machine learning method that works with 95% precision, I will be surprised. This is a very good precision. And it works in production, and it's making about like $6 million a year in ads revenue. Yes? Yeah, wrap up. Takeaways. You can read the takeaways. Yes. Yes. So first of all, tomorrow in Culture Club, I'm inviting a very famous machine learning researcher named Elad Yom Tov. He will be talking about improving information retrieval using social network data. Very important topic for us. And my next talk, which is actually about scaling up machine learning, is on February the 27th. It's actually in this room, but the venue is it's ACM meetings. So they hold their meetings once a month over here just in this building. And I was invited to give a talk on this topic. So if you guys are interested, I'll be happy to see you. Thank you very much.